Hey, hi everyone. Welcome to my YouTube channel. This is my first video on DSA. The topic would be recursion. Just a warm welcome to my YouTube channel if you're watching this video. The purpose of this video is to learn recursion as a concept. So myself, Indranil, I am a AI software engineer at one of the most reputed product-based companies, and previously I've been part of organizations like Adobe, InMobi, and Myntra. After having taken hundreds of interviews in DSA also as well as system design, I know exactly the points in which candidates needs to improve. So not only from an interview perspective, but also from a concept perspective, what is recursion? We will be deep diving in to this mystified concept in this video. So let's deep dive in. So just to reiterate, we would be doing hands-on recursion from the next episode of the DSA series. But on this episode 1, we would be studying it as a concept. You'd be understanding how to actually know whether you need to apply recursion to a problem. And if you find it useful, please do like the video, turn on your notifications, and subscribe also for more content on AI, DSA, and system design. So let's deep dive in quickly into the video. So what is actually recursion? So recursion is a task that calls a smaller version of itself. Okay, so if it is not clear, I will go into each step one by one. So let's move on to the next slide. So what are the two golden rules of recursion? Okay, so recursion, as you may have heard that recursion calls itself, as I mentioned in the previous slide. So it will call, let's say, a smaller version of itself, then that will call a smaller version of itself. And in this way, we would be having a base case. So the two golden rules are base case, where the recursion stops, and the smaller subproblem, in which we are actually breaking the problem into subproblems and call, let's say, having a recursive call one after another. So when to use recursion? So there are a lot of, I would say, concept-wise, you can have some identifiers by which you can know whether you want to use recursion for that problem, yes or no. So we will go one by one. So breaking into smaller subproblems. So what does it mean? So let's take some examples so that you are able to understand very easily. So let's say smaller subproblems. Just ask yourself the question, can the problem be actually broken down into smaller subproblems of itself? So what do I mean? Let's consider an example of, let's say, factorial of a number n. So what does it mean? It means product of all positive integers up to n. N is some positive integer you can mention. Let's say, for example, 5 factorial. It would be 5 into 4 into 3 into 2 into 1 equal to 120. So if you see the pattern, it's dependent on the till the previous step. So it can be broken down into subproblems. Let's say factorial, if 5 factorial can be expressed as 5 into 4 factorial. Okay, then again 4 factorial can be expressed as uh, uh, 4 into 3 factorial. So there is a case in which you can see that there it can be broken down into subproblems. Okay, so that is why in the case of factorial, you can apply recursion if you want. Okay, because it can be broken down into subproblems. So it's one of the identifiers. Let's take a counter examples. You need to actually print the numbers from 1 till n. Okay, let's say, for example, n equal to 5. Okay, so the output should be 1, 2, 3, 4, 5. So why isn't recursion a natural fit here? Because there is no smaller sub-problem here. Okay. So are you able to break down into smaller subproblems? No, because of the fact that here you know that you need to print 1, 2, 3, 4, 5. So n equal to 5, you need to print 1, then 2, then 3, then 4, then 5. There is no way, there is no such way you can break down into subproblems. It's just printing one by one. Even if you think there is a recursive version that actually adds extra function calls, overhead increases, but clarity doesn't. So you have to understand if you can actually break down into subproblems like the factorial case. And also as a general rule, use recursion when the problem breaks into smaller subproblems and prefer iteration when the problem is straightforward and sequential without natural recursive breakdown. And also, please do remember, check for efficiency. What do I mean by that? Let's say you can break down into subproblems of itself, but it's a huge overhead in itself. Let's say it's a huge factorial. Then it can be that your basically when you are doing this, you can run into some issues like stack overflow. If iteration is then simpler and cleaner, then choose it. Okay, let's say for the factorial also, if you let's say have a very high number, you need to check and understand the efficiency because recursion overhead can cause stack overflow. Okay, so this is one of the ways to identify the smallest subproblems. Next, let's go to the next step. This is the hierarchical structures. So what do I mean by hierarchical structures? Just ask yourself the question, does the data form a hierarchical structure? What does that mean? So let's say a binary tree traversal. So a binary tree node has a root, a left subtree, and a right subtree. To traverse the tree, process the root, then recursively move from one from in the left subtree and then in the right subtree. So you see there is a hierarchical structure because when you are moving to the root to the let's say the left node, then that becomes a root of the below subtree. So in this way, you have a recursive concept. So this is the hierarchy I'm speaking about. Or let's say there is a directory traversal. A folder can contain many files and subfolders. So it's basically similar, a nested hierarchical structure. As a counter example, it's basically going through a flat list or an array of elements. It's just, let's say, printing elements 10, 20, 30, 40. There is no concept of hierarchy or nesting in a flat list. So, just as a general rule, if you find that the data is naturally nested, like having a hierarchical structure, use recursion. And like in trees, graphs, directory structures, and prefer iteration when you want more control over memory or stack usage. Uh, if you have again reiterating the point where you have let's say large deep hierarchies, then stack overflow can happen. So be very sure that you want to that recursion can be applied, and also we are not going into a case where stack overflow can happen. Efficiency check, recursion does give cleaner, more intuitive code for hierarchies. But for very large hierarchies, there might be a chance, even if you can do by recursion, it might go into stack overflow, and basically you should prefer iteration. Okay, let's move on to the next step. So exploring choices. This is another way which you can identify which if you want to use recursion or not. So it's called backtracking. So let's say maze solving. As you can see, this is a picture of a maze, and you can have multiple choices. Let's say user begins at a starting point and has multiple choices to move here and there and basically reach the end goal. So you can follow a recursive path here. It's called backtracking. Let's say you move to one path, but that doesn't end, that does end in a wall. What happens? You come back and you take the next path. So it's a multiple choice, exploring choices. You're backtracking to the point. So you need recursion here as well. But let's say for a counter example, you have a linear search and you don't need recursion for that because you don't have multiple choices there. Okay, so this is a general rule. It's backtracking is recursion plus undo. You try one choice after another until you reach the target. Okay, so let's move on to the next slide. So again, one of the another way in which we can apply recursion to a problem is by divide and conquer. So let's say, for example, of a merge sort where you divide the array into halves. So whenever you are dividing the array into halves, what happens? They become arrays in itself. So again, you break it down. You break it down until you reach an end point in which you can't break it down. So it's a classic example of a recursion. Merge sort is an example, quick sort is an example, but let's say we are doing with the bubble sort. In that case, recursion doesn't actually fit, but because of the fact that in bubble sort, you are not breaking into smaller subproblems or doing divide and conquer. What you are doing is you are making a repeated process by which you are swapping elements and moving the largest element at the end. So it doesn't actually fall into the category of divide and conquer. So I hope you understand this point very easy, very well, that why we are using recursion here. So whenever there is a chance of divide and conquer, try using recursion. So let's move on to the next slide. Okay, so indefinite depth problems. So what does it mean? Let's say we have a tree, or let's assume we have a binary tree and we need to find the maximum depth of the tree. So we will go depth by depth. We don't know what depth it is. So we'll go depth by depth and we reach the depth, then come back again. Then it's sort of again trying out the maximum depth, because we can go in a tree. We can what do? We traverse. So once we reach the leaf node, that would be the base case, but that might not give us the maximum depth of the tree. So we have to explore the choices, other choices as well. So it's kind of choices also, but you can have like something of a depth. Okay. Like in nested comments as well, as you see in Facebook, Reddit, or YouTube. So it's a very similar thing. Counter example would be running a loop or for a fixed number of times. Example, printing a message 10 times. So why recursion is unnatural? Because the steps is known in advance and there is no smallest subproblem or branching involved. Iteration fits better here. Okay. So the thing to remember here is that you should be having recursion, but let's say it's a very the depth varies very large. Okay, in that case, again, Stack Overflow can happen. Okay, in such a case, you should be doing it with the iterative step and with explicit stacks and queues. We will um, explore this option in the next few episodes of this series, where we would get hands-on and explain each and everything step by step, doing hands-on. So right now we are focusing on the concepts. I hope this concept is clear to you guys. So let's move on to the next step. So pitfalls, what we say here, it could be infinite recursion. It could be that I told you that there are two golden rules, like it calls a smaller variant of itself and then a smaller variant of itself unless we reach the base case. Otherwise, it would be infinite recursion, right? There is no stopping. It will call itself. It will call itself. It happens when there is no valid case for itself, no stopping condition, or a wrong base case, then a wrong output would be coming. Or let's say you made a choice of recursion. It is an example of recursion, but the thing is that it 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 came to a fact where the recursion depth is so large that you ran into a stack overflow problem. That is, the resource limit was reached. So let's go example by example. So factorial, as I was telling, factorial of n is the product of all numbers from 1 to n. So we will have a base case of n equal to 0 or n equal to 1 and return 1. And for the recursive case, it would be like n into factorial of n minus 1. So how we are getting it? So you see factorial of 5 equal to 5 into factorial of 4, then 5 into 4 into factorial of 3. So in this way, we are breaking it down. So it becomes a recursive step like this, n into factorial of n minus 1, and the stopping condition n equal to 0 or n equal to 1, return equal to 1. Let's take a next example. Fibonacci, it's a very classic problem in itself again. So Fibonacci is a sequence in which each number is the sum of the previous two starting with 0 and 1. Okay, so what you are doing is it has the, so you see it can be broken down into subproblems again because it just depends on the previous two. So that is why Fibonacci n minus 1 plus Fibonacci n minus 2, because it depends upon the previous two. We are summing till each number is the sum of the previous two. So that's what we have done here with the base case of n less than or equal to 1, return n. But we will explore this problems in depth in the latter episodes. But here also I will deep dive into one problem and explain to you what concepts we have learned. But these are just examples that I am telling you so that you understand what we have learned till now. Next is a binary tree traversal. Again, as I mentioned, for a binary tree traversal, it has hierarchies. We can move to the left and then to the left. And basically, if we need to traverse it, let's say for an in-order route traversal in which we traverse to the left first, then the data, then the right. So we have a recursive process, and basically, this is a pseudocode for that. We will explain trees in later videos. It's just for example. Now, where does recursion shine in DSA? It's binary trees, backtracking, and divide and conquer, the concepts that we have already learned. Okay, we have already learned this concept. So next, let's move on to a quick checklist. So can the problem be broken into smaller versions of itself? Does the data form a hierarchy? Do I need to explore multiple paths or possibilities? If yes to any, recursion is a natural feat. But if iteration is simpler or input is too large and you can apply recursion to it, don't apply. Try for iteration. You will end up with stack overflow, that is recursion limit exhausted. Keep that in mind. Recap, base case plus recursive case. You have every recursive solution must have both, breaking big problems into smaller ones, where you solve the smaller version, then build back up. Things self-similar. If the problem of structure looks like a smaller version of itself, like factorial, trees, nested data, recursion is a natural fit. Check practicality. Recursion adds clarity for some problems, but if iteration is simpler and safer, like the resource limit exhausted, it can be a case, then prefer iteration. Always test with small inputs first, ensure base cases and stopping conditions are correct. So now, after learning all the concepts, we will focus on a problem. Okay, I will guide you how to approach this problem. This is a famous lead code problem, climbing stairs problem statement. So let's say you are climbing a stairs. Each time you have a restriction that you can take one step or two steps at a time. So find how many distinct ways you can climb to the top, n steps. So when this problem is given, clarify, uh, let's say if n is a positive integer, because those are base cases, right? So n steps means n should be positive because you are running up the stairs, so it can't be negative. So consider all base cases. Now just coming to the problem statement, if input n equal to 3, so then the output is 3. How? Let's say you take one step, one step, one step, one step, then two step plus one step. So you see it becomes 3. Okay, we will try to formulate how it can be a recursive problem by taking certain examples, and you will see that it falls into one of the concepts that we have earlier discussed. So let's move on. So while doing the so how we can identify that it is a classic example of a recursive problem? How? So let's say, what is your target? Your target is to reach the step n. Think in that terms, that you can move from one step to the other with a restriction. That is, you can move one step or maybe move two steps. So when you are at the nth step, so previously, where were you? You could have been at n minus 1 or n minus 2. Why? Because from n minus 1 only, you could have taken one step to reach n, or maybe you would have been at n minus 2 step and you could have taken two steps to reach n. So there are only two ways. And if you see here, if you can think, it's a classic example where you can break down into subproblems. So f of n. So f of n means that what are the number of steps till that point? What are the steps to reach fn? So total, basically the total number of ways to reach the step n. So that could be f of n minus 1 plus f of n minus 2. So did you understand how we reach this step? If not, let's again deep dive. So when you are at the step n, you could have reached that from n minus 1 or n minus 2, because from n minus 1 you took one step to become n. Again, from n minus 2 you could take two steps to become n. So that's the restriction of the problem, and there it symbolizes how can you form a recurrence relation and break down into some smaller subproblems. Here we are breaking down into smaller subproblems. So working example, as I mentioned, 3, then 4 equal to 5, 1 plus 1 plus 1, then 2 plus 1 plus 1. These are all steps: 1 plus 2 plus 1, 1 plus 1 plus 2, and 2 plus 2 plus 1. It should be 2 plus 2 plus 1. Sorry, it should be 2 plus 2. Okay, so because we are doing n equal to 4, so 5 ways. Okay, so let's deep dive into the code, Java code. So you are calling, let's say, with 3. So you are breaking down into client stairs n minus 1 plus n minus 2. We discuss the reconciliation. And for the base cases, return 1. So for one step, the how many ways you can do? Only one. N equal to 2. How many ways you can do? 1 plus 1, or just take two steps. Simple. So n equal to 2. So just two base cases. This is Java code. This is a C++ code. And you can just check this, and you can just check this as well. So conceptual fit with recursion, as I described, it breaks down into smaller subproblems, base cases, as I discussed, and recursive case. Each larger problem splits until reaching base cases. So this is a classic recursion problem tied to the concept of breaking into smaller subproblems. I hope you liked this video. Just please, if you like this video, please subscribe to my channel, like the video, turn on your notifications. I regularly, each and every week, share content on AI, DSN, system design, and next up would be hands-on recursion problem, as I had mentioned throughout the video, to beginner to advanced, and I would relate them directly to the concepts learned here. So please watch this video completely and learn your concepts. So thank you everyone. Bye for now. Let's meet in the next video.